Good morning. It's July 29th, and this is your daily brief in science. Here's everything you need to know. A high-stakes rescue mission faces a setback as Katalyst Space Technologies' Link satellite experiences thruster issues and begins spinning, disrupting the plan to lift NASA's Swift observatory to a higher orbit. Link is tasked with approaching, capturing, and elevating Swift, contingent on recovering Link and updating the mission plan as needed. NASA is backing the effort with around $30 million for a sub-year operation aimed at preserving Swift's science operations amid technical risk. Katalyst's chief engineer notes the rapid development increases uncertainty, but underscores urgency to elevate Swift. The principal investigator points to prior power and communications challenges, stressing that a basic, functioning spacecraft is essential for rendezvous and dynamic operations. Subsystems including communications, propulsion, and robotics are reportedly functional, with teams working to reduce body rates and stabilize Link using gimbaled electric thrusters. The plan involves updating guidance, navigation, and control to match the current configuration, then proceeding with an approach to Swift and a potential rendezvous. For ongoing updates, follow Katalyst's learnings and NASA's Swift blog, with links to Katalyst's mission page and the Swift mission blog. Despite the setback, both Katalyst and NASA remain hopeful that Link can rendezvous with Swift after implementing changes, with major subsystems reportedly operating normally. All major Link subsystems are reportedly functioning, with power positive and ground communications active. The collaboration features a rapid, under-1-year development timeline, highlighting the urgency and high-stakes goal of preserving Swift's scientific capabilities. Katalyst recently secured a $12 million funding round in June, supported by Fortitude Ventures and Geodesic Capital, with interest from U.S. military sponsors seeking a capable satellite servicing platform. A new nature study in the southwest Amazon reveals about 396 previously unknown earthworks across roughly 4,500 square kilometers, suggesting the Akwari civilization may have numbered between 24,000 and 30,000 structures across the region. LiDAR surveys uncover hundreds of large geoglyphs and extensive ancient roads tied to the Akwari, a polity that thrived roughly from 600 BCE to 8850. Earlier airborne laser scanning in year 2024 identified 432 earthworks in Acre and Amazonas, with 36 new ones, refining the mapped geographic extent and population estimates for the Akwari. The findings imply pre-colonial civilizations shaped soils and forest composition, challenging assumptions about pre-contact land use in the tropics. Most earthworks belong to the Akwari complex, a multicultural network with ceremonial or political centers rather than solely permanent residences. The piece serves as a research briefing that situates the nature study within broader historical and geographic scholarship. Compared with later mound villages from the 13th century onward, the Akwari centers show continuity in community organization and emphasize geoglyphs' ceremonial and administrative functions. If validated, the Akwari landscape would have supported large wooden longhouses, maize, manioc, squash, cotton fields, and managed fruit and nut-bearing trees, indicating long-term environmental stewardship. The cause of the Akwari's decline remains unknown, though the environmental impact remains evident in the landscape. The article underscores that the Amazon housed sophisticated pre-Columbian societies and calls for ongoing science journalism and support for research. Kernel density analyses suggest peak earthwork use around 100 to 300 CE, with sites overlapping, indicating coordinated gatherings across the landscape. Acknowledging canopy detection uncertainties, the authors call for further archaeology to refine dates, functions, and population dynamics across the Amazon. A new study proposes a global firestorm triggered by the Chicxulub impact as a central extinction mechanism for the dinosaurs. The researchers argue that a massive dust cloud formed when vaporized material re-entered the atmosphere, trapping heat and irradiating Earth rather than just causing regional warming or cooling. They describe immediate planet-wide heat from this dust layer as the primary driver, with fires ignited worldwide and lasting thermal effects shaping the extinction timeline. The model estimates about 1.6 trillion tons of ejecta created a global dust blanket that produced a prolonged thermal pulse. If confirmed, the findings could change how we understand the pace of ecosystem collapse and the duration of atmospheric particulates' impact. Ongoing fires and heat could have persisted for years, compounding ocean disruption and the collapse of photosynthesis. Spherules formed by atmospheric friction helped ignite fires, and most material remained as widespread dust rather than condensing into spherules. The researchers note that this scenario could help determine whether the mass extinction happened within hours, years, or decades after impact, and may explain why some species survived. The dust cloud's thermal radiation is highlighted as central to extinction dynamics, with fine 2.5 micron particles posing longer-term health and ecological risks. Fiery spherules and a fine dust vapor layer would have heated the surface and potentially caused rapid die-off of many terrestrial species. The study acknowledges the possibility of rapid but not instantaneous extinction, as dust would later block sunlight and cool the planet for years or decades, enabling a slow starvation contribution. The scenario blends impact physics with geological observations including spherule formation and evidence of extremely fine post-impact dust identified in 2023. A large multi-ancestry genome-wide association study meta-analysis across 11 cohorts from multiple countries identifies 26 independent genetic risk loci for fibromyalgia in about 2.56 million individuals, including 54,629 cases and 2,509,126 controls. The strongest association centers on a coding variant in the HTT gene, with carriers having about a 9% higher odds of fibromyalgia, or approximately 1.09. The study used a fixed effects inverse variance meta-analysis to combine data across cohorts and prioritize causal genes through literature review and flames/decode analyses. Experts say these genetic insights could improve future diagnosis and treatment and may intersect with Huntington's disease drug trials targeting related pathways. Prioritized genes with brain-related roles include HTT, DCC, MDGA2, and CELF4, suggesting links to neurodevelopment and pain pathways. Pathways implicated repeatedly involve pain processing and brain function, including CELF4, DRD2, CAMKV, MDGA2, and DCC. Researchers emphasize fibromyalgia as a biological condition, which could reshape clinical approaches and patient experiences beyond psychological explanations. Results reinforce a biological basis and suggest genetic overlap with lower back pain and irritable bowel syndrome, pointing to shared underlying mechanisms. The study identifies pathways that could inform future treatments, including potential relevance to Huntington's disease drug research, while noting the condition is not primarily autoimmune. A strong link was identified between fibromyalgia risk and the HTT gene, and a second variant affecting a receptor that regulates HTT levels points to potential drug targets. Tissue and cell type analyses show heritability enrichment in neural tissues and neuronal cell types, with the dentate gyrus among the strongest signals. A new study ties queen pheromones directly to how a wasp or bee colony evolves, showing that higher levels of queen-produced methylalkanes correlate with greater reproductive output and more daughters staying to help. Researchers identify methylalkanes as the queen signals that indicate reproductive capability and influence daughters' roles within the colony. The work, led by Callum Kingwell of Princeton Stree and Bill Wasislow, was published July 28 in Proceedings of the Royal Society B. Chemical analyses were conducted in the field using gas chromatography mass spectrometry to identify and quantify pheromonal compounds on live bees across their lifespans. Fieldwork focused on Megalopta genalis on Barrow, Colorado Island, Panama, using artificial nests and long-term observation to track daughters' fates and analyze pheromonal signals. The Panama study leveraged Barrow, Colorado Island's long-term field observations and live behavior sampling to study chemical signaling in free-living bees. Researchers from the Smithsonian Tropical Research Institute and Princeton University conducted a multi-year study on Barrow, Colorado Island, deploying artificial nests and recording bee behavior. Findings are interpreted as evidence that queen pheromones contribute to cooperative behavior and could stabilize nascent insect societies, marking the first identified queen pheromone in a flexible social insect. The work offers insights into the evolution of cooperation in insect societies and broader implications for evolutionary biology and animal behavior. The findings illuminate how nascent insect societies might stabilize and evolve toward greater social complexity, advancing understanding of queen pheromones in flexible social insects. Pheromone production depends on a dietary protein essential for reproduction, making it costly for the queen to falsely advertise royal status. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.